Okay, solving rational expressions builds on all of the key pieces from last unit. So we need to review and compare a couple of areas where you can make mistakes and where I need you to draw on past knowledge. We have solved problems with cross products where we've had fractions and things in the denominators. But cross products can only be used if you have fraction equal fraction. So in this case, we have a singular fraction equal to another fraction, and we could go ahead and use cross products to solve that. Now, rational expressions is the unit that we just got done doing. And here, we needed to make that common denominator. And we did that by multiplying by 1. And remember that we built 1 in such a way that we weren't, changing our problem. And because this is an expression, which means there's no equal sign, we have to be very careful that we don't change the value of our fractions. Now, where we're going right now is this, rational equations. It's equations that have fractions on both sides, so they're going to look a little like our cross products, but there's this plus here. So we cannot cross multiply, and we need to solve it. We were missing the equal up here, but now we have it. So here we can actually solve for n. We can get a value for n. And this is a very clear-cut 8-step process. We're going to go through an example with these, but just to run through them quickly. We are going to factor the denominators if necessary. We're going to determine the least common denominator. We're going to determine any restrictions on the variables. Anytime you deal with fractions, there are things that the variable can't be because you can't ever have 0 in the denominator of your fraction. Then we're going to multiply both sides by the least common denominator. We're not going to make a common denominator like we did with rational expressions. We're actually going to clear out our denominators. We're going to do our canceling. The denominator should disappear. We're going to distribute, multiply, combine like terms with what's left. Go ahead and solve for the variable, which is a straightforward Algebra 1 problem, usually. Might require quadratic, might require factoring if you have a squared term. And then we're going to check to make sure the answers are possible. Check against your restrictions to make sure that your answers don't include restrictions. And you could always put your answer back into the original and see if it works. So what does this look like? So here's our example. 1 over 6k minus 1 over k squared equals 5 over 3k. First step is to factor the denominator. But I don't have to here because my denominators are factored. So now I have to determine the least common denominator. And the least common denominator between 6k, k squared, and 3k is going to be 6k squared. Now, we're going to determine any restrictions on the variable. So what we have to think at this point is what value of k would make the denominator equal 0. And since I have 3 denominators, I'm really thinking about 3 little baby problems. If k squared equals 0, if 3k equals 0, and 6k equals 0, each of the denominators. So you would actually go through and solve them. And in this case, they all come out the same. They wouldn't necessarily, but if k were 0, those denominators would equal 0. But since our denominator can't ever be 0, this helps us find our restrictions. And so our restriction is to say that k can't be 0. So if I get down and I do all my solving, and one of my answers is k is 0, I cross it off because it will make my original statement false. If it's my only answer, I write no solution. If I have 2 potential answers, I cross the restricted one off and keep the other. So now I'm going to start with the actual process. So now I'm going to multiply both sides by that 6k squared common denominator. And that number is right here and right here. Notice I protected my original in parentheses because I want to make sure that I distribute correctly. right here, and right here, keeping my parentheses around my original. Now, if you want to think about those common denominators as being over 1, that's fine. But what I've created now is a multiplication problem here, multiplication here, and multiplication here. And we know if we have multiplication with fractions, we can take our canceling pens and we can start canceling. And so 6k squared and 6k will cancel and we'll leave k in the numerator. K squared and k squared cancel, and k and k squared cancel, leaving k. 3 and 6 cancel, leaving 2. Now, what does this look like? I'm left with k times 1 minus 6 times 1 equals 2k times 5. And what is left of that common denominator is right there. So now I have a basic problem that I just need to clean up. I've got k minus 6 equals 10k. I do recommend you leave those ones in there, and I will show you another example later why. Solve for the variable. Negative 6 equals 9k when you subtract k from both sides. Divide both sides by 9 and make sure that you do this step right here. Lots of people go the wrong way, and then we always present fractions in lowest terms. Negative 2/3. Negative 2/3 was not my restriction. My restriction was 0, and so that is my answer. Now let's go ahead and look at an example or two. In this case, if you want to think about it like this, my least common denominator between x, 1, and x is x. My restrictions are that x cannot be 0. If x is 0, this denominator and that denominator will equal 0, and that can't happen. So now I will color code this because my task is here to multiply all of this by x and to multiply all of this by x. So I'm going to have 5 over x plus 1 over 1 is equal to 1 over x. There's my original. And if I think about how this gets distributed, I'm going to have an x in each numerator. When I cancel, x and x cancel. Nothing cancels in the second piece. X and x cancel. And I'm left with 5 plus 1 times x equals 1. Now this is a key place where I want you to leave those, be aware of that 1. The temptation is if you cancel both pieces to have 0. It disappears. But remember, a number divided by itself is 1. So here I have 5 plus x equals 1. Subtract 5 from both sides. X is negative 4. Check my restrictions. And that answer is valid. If I wanted to check my work, what I would do is I would put 5 over negative 4 plus 1 over 1. Does that equal 1 over negative 4? I just substituted the negative 4 wherever there was an x. We add fractions by making a common denominator. And this statement is true. So we know our answer is right. Now let's look at another example. Now this one looks more complicated, but I have to factor first. Greatest common factor between a squared and 6a is a, and that leaves a minus 6. This one factors in exactly the same way. You have to factor so you know what your pieces are and so that it's multiplication so you can cancel. So my least common denominator here is a minus 6 times a. Now if I think about each of these pieces, in this first piece, if a, okay, now you're thinking, here's your little thinking bubble, a minus 6 equals 0. Well, that happens when a is 6. So my a can't be 6. What would make this equal 0? Well, the 6 would, or if a is 0 would also, because this part would be 0 and the whole thing would go to 0. The third piece is exactly the same. So now I'm going to go ahead and multiply everything by that least common denominator. Okay, I'm going to go ahead and take the time to color code it for you again. So I'm going to put my original down, 1 over a minus 6 plus 6 over a times a minus 6 equals 1 over a times a minus 6. Common denominator, a times a minus 6, a times a minus 6, a times a minus 6. Now we're going to go ahead and cancel. A minus 6 and a minus 6 cancel. A and a minus 6, a minus 6, a minus 6, a minus 6. What am I left with? I'm left with 1 times a plus 6 is equal to 1. So a plus 6 equals 1. Subtract 6. A is negative 5. I will put the last two examples on